I'm going to take a detour for a second, and I'm actually going to take a detour into a major subject and a major point of computer science, and that's this idea of computational thinking. You have some background now in coding in Python, and we're getting into the point where we're going to be talking about control flow using things like conditional statements and loops, right? We've already talked about conditional statements. And I want you to start having a fuller understanding of what really computational thinking means, and particularly in terms of the work we're going to be doing and what kind of process we want to go through as we do this work. So let's take a step away from Python for a second and just talk about what computational thinking means and what it looks like. So I want to start with a problem. And the problem is this. What might be some ways that you could add all the numbers from 1 to 200? Now, if we start going through this process, we might think of, okay, maybe I'm going to add 1 plus 2 plus 3 plus so on, 199, 200. That's going to take a long time. Now, ideally, you've already noticed with Python and with some programming, we can do it a lot quicker. But let's assume for a moment we weren't going to use a calculator or a programming language. We were just going to do it by hand. And what we want to start thinking about is how might we do this in a more efficient way? I mean, a joke kind of in computer science is computer scientists are by nature lazy because we're always looking for a faster, easier way of doing things, which I don't know about lazy, but that's true. We do look for efficiency. We do look for trying to find the best way of solving a particular problem. So this is what we call, this first solution here is what we call the naive solution, which sounds pejorative, right? Sounds like we're saying a negative thing, but it's just really what we call the first thing you think of. And often the naive solution, finding it, thinking about it, is the step for finding the best solutions. So it's not a bad thing. We often want to start with the naive solution. Sometimes the naive solution is the best we can do, and that's okay too. And now we want to just play, right? We want to just say, what are some other ways to add these numbers? We could do 1 plus 2 is 3, 3 plus 4 is 7, 5 plus 6 is 11, and start adding those numbers again, kind of breaking the problem down and doing partial sums. I'm not sure this saves us a lot of time, but it gives us another way of maybe a slightly better solution than what we had before. I'm going to skip that. Okay, so what might be some ways that, so let's think about the problem, but let's think about it in a smaller slice. Let's think about what are some ways that we could add all the numbers just from 1 to 10, right? Because I think if you take a larger problem and you cut it down to a smaller version, it's often easier to think about the total scope of the problem. So this is like a microcosm, right? This is a smaller version. If we skip the methods we already talked about, right? 1 plus 2 plus 3 plus 4 plus 5 plus 6, so on. If we don't do 1 plus 2, 3 plus 4, so on and so forth, and kind of like a tree structure, what are some other ways we could think about adding these numbers together? Well, one method we might consider is what if we pair the first and the last number together? 1 plus 10 is 11. 2 plus 9 is 11. 3 plus 8 is 11, right? So we're making this rainbow structure. You might call it, it's commonly referred to as a Gaussian sum, right? Gauss was sort of credited with coming up with this algorithm because this is a pattern that we're noticing, and there is a process we can go through for adding large sums that becomes very quick, right? And when we're doing this sort of cognitive process of looking at a problem and looking for these patterns and trying to come up with solutions, right? We want to ask ourselves kind of critical questions about it. If this is true for 1 to 10, for instance, how would this be different for 11 through 20 or 21 through 30, right? How would this change depending on how the problem changed? And what we find out is while the sum changes, obviously, because we're dealing with different numbers, the pattern actually doesn't. And so the universality of that pattern applying to a bunch of different subsets of our larger problem gives us some hope that, okay, maybe this is something, right? Maybe we found a pattern that lasts. So if we jump back to the larger problem, and we apply this pattern that we've seen, we find out that 1 to 200, 1 and 200 is 201, 2 and 199 is 201, 3 and 198 is 201. Okay, here's our pattern, right? What do we do now? Well, maybe we ask the question, how many pairs are there like this? And we quickly find out that if there are two numbers from the set and each are paired, then that's maybe half as many pairs as there are numbers. So 200 divided by 2. We do some quick math, right? So we can figure out, okay, if we have 100 pairs like this and each pair adds to 201, we can actually figure out pretty quickly what our sum is. So this is what we call, what we've done now is we've identified patterns, and now we sort of want to abstract that. We want to take a step back and say, okay, how could we kind of describe this in an abstract sense? Let's not talk about necessarily 1 through 200, right? So the first thing we did was we added the 201, and we found a sum that was repeated over and over again. And then we found out how many pairs of there was. We did that math, and we ended up with 20,100. So if we generalize it, we can say for any range, 1 to some number n, the sum of all of those numbers can be found by n plus 1, right? So 200 in our case plus 1 times half the number of numbers there are, so 200 divided by 2. That may seem like a large jump, right? To go from this kind of like, we're talking about this particular problem into this thing that looks very algebraic. But it's this kind of process of looking at something specific, generalizing it, abstracting it, right? Turning it into abstract steps, finding patterns that builds algorithms and can help us build our code and solve coding problems, challenges, what have you. And the question then becomes, okay, can we replicate this for 1 to 5,000? Sure, right? No matter what, the problem, not no matter what, but in many cases, right? So we can apply this algorithm to many situations. We get this very fast way of solving this common problem that we can apply to many different things. So I want to break this out now into generalized steps. Let's actually go to the steps. We add the first and last number, right? Does it matter what those numbers are? Maybe a little bit, but within a range, right? There's a lot of sets for which this works. We divide the total number of numbers in half. I can see my face is in the way here. Sorry, let me move the video. Actually, I'm just going to turn my video off for a second so we can see the rest of this show clearly. We're going to add the first and last number. We're going to divide the total number of numbers in half. We're going to multiply the result of step 1, adding the first numbers, with the result of step 2, dividing and multiplying by half the numbers. Now, as we go through this sort of algorithm design process, one of the things we need to do is we need to question. We need to be critical of our process. We need to test some of our assumptions and ask questions like, does the range of numbers increase? What if the range of numbers doesn't increase by 1 each time? If the set doesn't increase consistently, if the set contains duplicates, the range doesn't start at 1. Are there other patterns within these sort of questions that we can identify, or does this break our algorithm? Are these cases where we can say, yeah, our algorithm will not work for this case? And that's okay, by the way. I'm not saying that's a problem. I'm just saying it's important to know the limitations of your algorithm. So let me just recap quickly what we just did, what our brains were doing through that process. We broke the problem down into smaller, more manageable problems like adding pairs or looking at just 1 to 10. We identified the repetition of 201. We took advantage of the fact that pairs add to 201 and there are half as many pairs as numbers to create a formula and eventually an algorithm. We listed the steps, and we looked at what problems we might face moving forward. This is computational thinking. This process is computational thinking. And the short version, right, the keywords for each step here is decomposition. We did decomposition to the problem. We decomposed the problem, I suppose, breaking it down into more manageable steps. We identified pattern. We did pattern recognition. We did abstraction, meaning we moved from the specific to the general, right? We weren't just talking about 1 through 10 or 1 to 200, but maybe all ranges of numbers that kind of behaved in a similar fashion or had similar context. We sequenced it, right? We did step by step. Do this first, do this second, do this third. And finally, we did evaluation and debugging. How would this work in this case? Are there errors are there issues if the set looks like X, Y, and Z? And you can actually cycle through this process a number of times, right? You might get to evaluation and debugging and realize that, okay, you've found a solution for a particular set, for a particular problem, but that particular problem, when you did your decomposition, is only a microcosm of the larger problem, and you actually have to do some adjustments to be able to take in the totality of the larger problem, right? You have to do some things. Now, in our case, that's not the case. 1 through 10 and 1 through 200 or 1 through 5,000 all work the same, but you might find that your solution doesn't actually solve for the larger problem. And that's where evaluation and debugging and then cycling through, iterating, if you will, through that process really helps. Okay, so that's computational thinking. So as we go forward in our course here, and we face problems, I want you to think at least a little bit about these steps that you're going to go through. I want you to think about doing decomposition of the problem, making up smaller problems. I don't know why I feel it seems weird to say decompose the problem, right? I want you to think about what patterns you find particularly. That's a really important step for us is identifying those patterns and then trying from those patterns to abstract into some sort of algorithm, some sort of system that we can consistently follow. Because once we get there, we know now it's very easy to hand steps to a computer and have it reliably follow those steps over and over again, right? That's the key juncture between what we're going to do as computer scientists and what the computer is going to do. We're going to do the part where we come up with the rules. We come up with the steps we want the computer to do, and then the computer will reliably, consistently follow those steps. So if we can work in conjunction with the computer in that way, then we'll be successful in solving the problems we want to solve. All right, that's our foray into computational thinking, which again is a tangent only so far that it's not Python, but it is really actually core to what the learning and the practice we want to be doing moving forward. So as we think about all the work we do, we want to think about it through this lens of computational thinking. All right, good job.